started here. We want to welcome you all to the Cemex Education Lab that we're putting on today and tomorrow. My name is Corey Zollinger. I am the Director of Infrastructure Solutions for Cemex. We're very excited for y'all to be here. We've got some fantastic content throughout the rest of today and tomorrow. I want to welcome you to that. Today we're very delighted to have Randy here with us. We're going to cover cool pavements, climate, and urban heat islands. As I mentioned, my name is Corey Zollinger, and I've got Randy Kirchain here. He's a principal research scientist with the Massachusetts Institute of Technology, and this content is really cool. So sit back, listen, and enjoy. And at the end, we'll have Q&A where we can discuss different things you might be interested in. So with that, Randy, take it ahead.
Thank you, Corey, and thanks for the opportunity. Again, my name's Randy Kirchain. I'm the director of the Concrete Sustainability Hub at MIT, and I'm going to share with you a little bit about some of the things that we've learned about cool pavements, how they play a role in affecting the urban heat island, and also I think one of the things that's surprising to many audiences is going to hopefully convince you by the end that cool pavements are things that not only cool the neighborhood, but actually are important for cooling the climate overall as well. So we're going to take a little bit of a deep dive about cool pavements. There's this technical jargon term called albedo. I'll define that for you. And then we'll talk about how they also impact the global climate. And then I'm actually going to hand it back off here to Corey, who's going to talk to you about some of the ways that we can create these kind of cool surfaces. Whether, when you hear the term pavement, you might think of roads, but we're talking about really any horizontal surfaces, and in particularly any horizontal surfaces that are adjacent to buildings is where this matters the most. So why do we care about cool pavements and cool surfaces? I think that most of us are generally aware that we're seeing some of the acute effects of global climate change already. This headline here from the recent UN climate report saying that once in 50-year heat waves are basically happening every decade now. And these effects are especially felt inside urban settings, where we see this warming is intensified by the urban environment. Recently, statistics came out that we're basically seeing 3 times as many extreme heat events here in the United States as we were seeing 50 years ago. So those extreme heat events have very real consequences. It's not just uncomfortable, but there's many different things we could hit on here. We wanted to spend most of our time talking about the solutions and what their effects are, but just to give you a sense of why we might care about this, 2 key facts come to mind. One is extreme heat leads to significant increases in energy consumption. That's probably fairly obvious to folks, but about every degree increase in air temperature, we see about a 2% growth in electricity demand. And so as we see more warming and more extreme heat, correspondingly, we see much greater demands on our grid and therefore the emissions that are associated with that. One of the things I think that's that's often overlooked is the health consequences of extreme heat. This is a graphic. It's a couple years old that was put out by the National Weather Service, and you'll see the headline there is sort of weather fatalities. I was hoping for an updated one. There's not an updated one for probably a number of reasons, but anyways, the 2020 data is still sufficient to make our point. So we see fatalities there from things that we might expect. So we see tornadoes, it's the 3rd one over. Hurricanes is the 4th one over. We see flooding there is the 1st, but you might notice that when we look at the 30-year average, that's the yellow column there, the largest number of weather-related fatalities is actually associated with extreme heat. And if you look into this a little bit, many experts believe that this is actually underestimated because oftentimes this depends on the cause of death actually being listed as heat, when someone may have had a heart attack that was caused by heat, but it might get not listed as heat related. That's not going to be the case for things like flood or lightning. Those, is somewhat more obvious what the direct connection is. So this is actually probably underestimated. So it's a significant health-related consequence. So if this is something we should care about for whatever that reason might be, global climate change, energy emissions, energy consumption and emissions, or health, so what are some of the things we can do about it? And there are many different solutions out there. We see things like AC and cooling centers that are being developed. Obviously, vegetation is an important strategy in any kind of urban environment. And we're gonna talk about this third option here, which is cool surfaces. I mostly have this slide to sort of make the point that in talking about cool surfaces, we're not in any way trying to say that communities shouldn't be pursuing these other solutions as well. It's just that there are only limited areas that can be vegetated, right? And so that you can have plants in place. There need to be hard surfaces in any kind of urban setting. So what can we do about those surfaces? There is one small other point that is some interesting, relatively recent research, is that it turns out that vegetated areas actually don't work as well when you're in the middle of extreme heat events. And that is normally because extreme heat events are often accompanied by extreme dry. And it turns out that what the vegetated areas are helping with is evaporation. And so if you're in a dry period, they're actually contributing less to cooling at the time when we need them the most. So again, not to say we don't pursue that strategy, but what about our hard surfaces? And it turns out that there are some things that we can do about those hard surfaces. So what is a cool pavement? A cool pavement is sort of self-defined. It is a pavement that's going to reflect more energy, it's going to store less heat, and therefore it's going to have lower surface temperatures, and as a consequence, contribute less to heating of the local neighborhood. This is a little picture here. I'm going to show you a number of these. This is just sort of the first one. This came from a Lawrence Berkeley National Labs photo that they had done. So the sort of image in the back is obviously a photograph of a road where we happen to have both a lighter colored road in the closer to the front of the image that happens to be right next to a darker colored road in the back. And then we have an IR image of that same section there, and you can see how much hotter the road in the back. The sort of the lighter color here means higher temperature. And so that's just sort of a visceral example of how significant these effects can be. And we'll show some more quantitative data about that going forward. So one term I'm going to use a lot in talking about cool pavements or cool surfaces is this sort of technical term called albedo. So generally a lighter colored surface is higher albedo. A darker colored surface is lower albedo. And albedo is just this jargon term for the fraction of energy that a surface rejects, basically reflects out. Okay, so higher number means more energy is reflected back out into the atmosphere. Lower number means that it is absorbing more of that. And just to kind of put some numbers to it, the Earth's average albedo is about 0.3. So in other words, of the energy that's coming in, about 30% of it is held and about 70% of it is sent back out into the atmosphere. By comparison, a concrete surface comes in at about 0.4 and an asphalt surface comes in at about 0.1, meaning so that it is, the asphalt surface is capturing a lot more of that energy than a concrete surface is. And actually, here's another, this is somewhat more quantitative one, example of that. This is location of that image. That one is Arizona. And so you can see this is a concrete parking lot and an asphalt road that's right next to it. You can see more than a 20-degree difference between the two attributed to this effect of albedo. So you can start to see that this difference in albedo can have a very significant effect in the amount of energy that's essentially being stored locally, right? And you know, the example that I usually give to folks, a lot of times maybe don't have quite as much time as we do today, so to try to make this point really quickly, I think that most of us may have had some interaction with this at a beach. So my example is, if you're at the beach and you're like walking back to the car and you're trying to make the decision whether to put flip-flops back on because the beach is pretty hot, when you get to the parking lot, you put the flip-flops on, okay? Because we've all run into this effect that the parking lot is considerably hotter. So that's what we're seeing right there. So maybe it's good that we could accomplish this higher albedo. We can reject more of that energy back out of the neighborhood. So what are some of the ways that we can accomplish this? And fortunately, there are a number of technologies. Corey's going to come back and tell you about some more specific implementations about these. But at a high level, there are essentially 4 different things that we can do. So we see experiments going on, particularly here in the Southwest, so in California, Arizona, with the first, which is essentially to put reflective coatings to coat an already existing dark surface. Beyond that, our solutions are essentially to change the materials that are in play. So we can go to more reflective aggregates, which is shown in the second column here. We can go to other types of binders, and then ultimately we can change the material that's in play in that surface. So again, as I mentioned to you, concrete itself tends to have a much higher albedo than asphalt, so we can make that material switch and gain these benefits of storing less energy in the environment, in the local environment. One point that we often get asked about in this context is that, doesn't the albedo of these surfaces change over time? Because I think most of us probably observe this more acutely when we look at an asphalt surface. So in other words, you've seen a brand new paved road and it's like really, really dark. And over time, it does become more gray, right? Probably less obvious to most folks is that when we look at a concrete surface, it starts very bright and over time also tends to become darker. There has been enough quantitative study over this. So essentially the question that we often get is, okay, so those 2 surfaces are different at the beginning, but don't they just become the same over time? And the fact is that's not the case. While they approach each other, on average, a concrete surface maintains a considerably higher albedo than an asphalt surface does in order to kind of retain these benefits over time. The other thing that you may or may not be aware, so if we're talking about a roadway application in particular, one of the ways that roadway is maintained over time is to essentially resurface it, to smooth out that surface. And so what you'll see is basically a reset of that albedo about halfway through. So the concrete is sort of swooping down, we have that resurfacing, and then it jumps back up. Same thing happens through an asphalt pavement's life. It sort of is drifting upward, becoming more gray. But as all of us know, eventually that gets repaved in one way or the other, and so you get this reset. And so when you look over time, we consistently see a higher albedo associated with those concrete pavements than with asphalt pavements. I promised you we would get more and more quantitative about this temperature difference, and sort of this is the apex of this. This is some testing that has been done in Phoenix of another sort of lucky place where there happens to be, there's actually 3 types of road here, even though in the image it looks like 2. So there's the concrete that is fully, concrete surface road on the left. And then on the far right is an asphalt road with an asphalt surface. What you can't see is there's a couple of lanes in the middle, which are actually a concrete paved, but then have had a layer of asphalt over the top. So that's why in some of the plots on the right, there are actually 3 columns. But the bottom line for these plots is essentially tried to be summarized in the red numbers across the top, which is, and I'm realizing now that in our setting here, folks in the back are probably unable to read this. So let me just, so what we're looking at here in the red numbers is the temperature difference, average temperature difference for these that were observed over about a month's time frame. And so the sets of columns are at 5 o'clock in the morning, basically at noon, at about just after, and then a couple of points in the afternoon, with the far right being at about 2:30 in the afternoon. And so what you can see is that even at 5 o'clock in the morning, we're averaging somewhere in the 1 to 10 degrees difference between these. And then that grows to somewhere at about 5 to 10 degrees difference. The upper plot is for the travel lanes, basically where you have cars. Essentially, what a car does to a road, if you think about it, is essentially blow the heat, right? It's essentially constantly driving convection across that road in order to cool it down to some degree. But even with that, we're seeing, on average, about 10 degrees difference in heat. The lower plot is for the two shoulders, the two areas of the road that don't get that constant convection being driven across them. And what you can see in that case is by the middle of the day, we have almost 20 degrees difference in the two. So substantially different amounts of heat being held in those neighborhoods. So hopefully that kind of makes the point that changing albedo changes that local temperature considerably. So the other question that we have often received is, okay, so that's great, but am I doing this at the cost of the global climate? Okay, and so this is what we in particular have been researching here at the Concrete Sustainability Hub. And there's sort of 4 mechanisms that I wanted to talk to you about that influence that question. So how do these changes in albedo change both the urban climate and the global climate? And that comes about in 4 different ways. So the way that we've essentially been talking about so far is the second one, which is this urban heat island effect. In other words, it changes the local temperature. Now, the way that affects the global climate is actually through the third column there, the one that's just to the right of it. So if I'm increasing the temperature in a local neighborhood, what am I doing? I'm driving up the use of air conditioning in that neighborhood, right? And so that then unless we're in a completely green grid, that's going to drive greenhouse gas emissions that are associated with it. The other way is that changing that pavement affects the global climate is the first one. This is a really jargony term called radiative forcing. I'm gonna explain that to you in just the next slides. And then the last one, which is really unexpected, I find, with most folks, is that, believe it or not, the characteristics of that pavement actually change the fuel use of the cars that are driving on that pavement. And we have this, we call it pavement vehicle interaction. Also kind of jargony, but also fairly self-explanatory. The pavement interacts with the vehicle. And so we're going to unpack all of those. One small point about that probably have made it kind of in the negative here. So the middle two are effects that are primarily concerns in an urban setting. Probably the more positive way or way to frame that is the 2 effects that happen on the end. So this radiative forcing, this pavement vehicle interaction, they happen no matter where this road is. This road could be in the middle of the desert or in a forest. Both of those are climate-related effects that a road can have. So let's start unpacking those a little bit. This one I've kind of already touched on, that higher albedo affects local urban temperatures. One question that we have gotten about how universal this effect is and about whether or not it leads to other derivative effects that might offset it. So one of the things that we have done through a group at MIT that specializes on climate modeling, we actually had them look at a case where we took all of the urban areas in the United States and essentially increased their albedo in a model, right? And then we simulated what would that do to the climate. The reason for doing this is because there was concern that, okay, yeah, we might be lowering the temperature in the urban area, but does that lead to derivative effects? Does it lead to like more rainstorms, less rainstorms? How does that offset things overall? And what the group found was that those things, there are changes that result of it, but in net, there are benefits across the board. So across all the U.S. urban areas, we saw an average decrease in urban temperatures of about 1.5 degrees. So you see that 1.5 in Los Angeles, dropping down to about 1.3 I should say that's the average change in the summer. Now, that doesn't sound like a lot, but what's, I think, really interesting are the other two columns. So you see an average drop in about 40% of those extreme heat events, so those heat waves, and about a 50% drop in the number of high heat index days, so days where the heat index is well in excess of 100 degrees. So this is one of the things that I have found is kind of tricky when we talk about climate change, is that a degree matters because a degree translates also into significant magnitudes and variation, and so it affects the peaks a lot. So that 1.5 degrees actually translates into some really significant overall effects. So that's sort of that second column about urban heat island effects. So what about these others? So let's talk about this really kind of fancy term, radiative forcing. So in order to explain that, let me just give you a real cartoon look at, so what is the greenhouse effect? So what is global warming or global climate change all about? So we have the Earth, and energy is coming in from the sun, and we have this blanket of gases around the Earth that lets that energy in, and then it reflects off the Earth, and some of it essentially gets caught inside that greenhouse. You park your car outside, you experience a little micro example of that. Energy comes in, the reflected energy doesn't have quite the same oomph, and so it gets trapped in there. So at a real cartoon level, there are two things that drive this. Essentially how thick the blanket is, right? So if it's holding more of it in, and that's what we mostly focus on, right, is these emissions of greenhouse gases, and they make that blanket more able to hold that energy in. The effect that we're talking about today is one that often doesn't get looked at, and it is if we reflected more of it back out, then you would hold less in, okay? Does that make sense? So if we fire more back out at that blanket, more of it goes through and less of it stays in. That's this albedo effect. You can imagine in my car example, if you have white seats, then you're gonna essentially reflect more of that back out of your car than if you have dark seats. They're gonna hold more of it in. The balance between these two, between how much comes in and how much stays in the blanket is referred to as this radiative forcing. And so it is radiative energy that's coming in that is forcing change in the atmosphere. So it's this radiative forcing. And so the way that albedo is relevant to this is essentially what I just explained. If we can make more surfaces brighter, then we can drive more of that out. It will shift that radiative, that balance more in a favorable state, and so therefore it has positive climate effects. What we have done to understand this is basically we've built a model that allows us to account for how a change of albedo at the surface affects that balance. And we can apply this really anywhere in the world. This is obviously a map of the US and how that effect changes across the United States. And what we've done in order to try to make it a little bit more meaningful is, so if there are these two effects, right, how thick the blanket is and how much we're going to shine at that blanket, we could talk about the albedo effect in terms of how it's effectively how much thicker or thinner we're making the blanket. So in other words, what we're going to do, what these numbers represent is how much CO2 we've kind of avoided correspondingly by changing how much gets shined at the. Does that make sense? So in other words, if we could take that much CO2 out of the atmosphere, it would have the same effect as shining that much back out at the blanket. The reason for doing that is because we always talk about we talk about global warming effects in terms of CO2 emissions. That's the common metric. So we've tried to develop a way to essentially take this effect, which is quite different, but put it into those same terms. So that's what you're looking at here. This map is showing us essentially if we were to make a 0.2 increase in surface reflectivity of all the pavements across the US, what would be the corresponding savings in terms of CO2 equivalents, essentially thinning that blanket, if you will, from making that change. And so it translates into about a little over 17 million tons of CO2 equivalents a year, which is about the same as taking about 4 million cars off of the road. So it's not an insignificant effect. It occurs no matter where we are. So what about these other effects? So we'll talk about the last one first here. So I find it comes as a big surprise to a lot of folks that pavements actually change the way that you use fuel. And this comes about through two different mechanisms. I have three here just because I often get asked about the third. So the first one is the roughness or the smoothness of the road. So basically the rougher the road is, the more time your wheel is doing this as opposed to going forward. The reason I have the third one down here is I often get asked this question, okay, but we want a road to be rough enough to stop on, right? And that is the answer, obviously, is yes. But the roughness that we're talking about is the magnitude that essentially causes your shocks to engage, right? So we're talking about potholes, sort of waviness in the road, that order of magnitude. The roughness that matters for stopping, the industry refers to as texture. So that's the pebbliness of a road. You know, the thing that skins your knee if you fall on the pavement. Okay, so we're not talking about that roughness. We're talking about the sort of larger magnitude roughness. And a little fact that we have up here is about a 10% decrease in that roughness translates into a 1 to 2% change in the fuel use of your car. And it turns out that basically a concrete pavement tends to stay smoother longer over time than an asphalt pavement does. You might remember in that plot that I showed you how the albedo was going down and then got reset, as opposed to on the asphalt pavement it was going up and then got reset. That reset is happening because of this. It's because your local jurisdiction or your state is repaving that road to account for the roughness that has been increasing in it. The other effect that the way that a road changes fuel use is through deflection of the road. So again, this is something that tends to be really surprising to most folks, because when you or I walk on a road or we walk on this concrete surface here, it is essentially perfectly rigid. But when you put a car on it, and especially when you put a truck on it, it actually bends a little bit. And so the physics of this isn't quite accurate, but the mental image is pretty good, which is that essentially you're always driving up a tiny little hill. And the steeper that hill is, the more energy that's being used. I think I have next slide. Yeah. So again, beach serves as a pretty good example of this. So obviously the magnitude of this effect is much smaller on a road than at a beach. But if you think about the amount of effort it takes to walk or run on a beach as opposed to walk or run on a sidewalk, that is very much like the physics we're talking about here. I'm essentially using a lot of energy on a beach to deform the surface as opposed to where I want that energy to go, which is in driving a vehicle forward. And it turns out that a concrete pavement obviously is much stiffer. This effect is even more extreme the slower the traffic is going. So in urban settings, it's an even bigger deal. And then finally, I mentioned that sort of it was actually the third one in the plot, is what about how the changes in the surface affect the energy use of the buildings adjacent to it. So there's some complexity here. So what I've referred to so far is that the changes in that surface affect the temperature in the neighborhood. And so a cool pavement obviously has benefit in that way, in the sense that it reduces local temperature and therefore reduces air conditioning demand. There is a negative side effect that can happen there as well. So they're sort of have the nice little sun in the upper right, and then there's three sets of arrows going on. The really steep one is the one I already talked about, the radiative forcing. So that's the energy going back in the atmosphere. The little wavy ones down at the bottom, those are supposed to represent the fact that there's less energy being stored, and so the average neighborhood is cooler. There's a negative effect, though, which is that depending on the angle there, some of that energy will actually get reflected onto the building itself. So in order to make sure that we're accounting for all of those things, we've actually built up models of all of these effects, including we've basically simulated these effects for actually tens of thousands of neighborhood configurations. So tall buildings, short buildings, close together buildings, wide streets, neighborhoods with yards, without yards, and we can account for all of these kinds of effects. And sort of the long and short of it is that we have shown that basically implementing cool pavements, as I mentioned before, always cools the neighborhood. So those health effects, those health benefits, those are there. And what we've also found is that in the vast majority of the cases, 80, 90% of the cases, making that change also leads to net climate benefits. So you end up with reduced fuel consumption of the vehicles, you end up with reduced energy consumption of the local buildings, and that's even accounting for all of those kinds of effects. And also we have this radiative forcing benefit as well. So just kind of bringing this all together, and then I'm going to hand off here to Corey, and he'll talk about some ways that we can actually implement these in the real world, is just to kind of remind you that albedo is this measure of the fraction of energy that's essentially being reflected back from the Earth's surface. So generally speaking, lighter surfaces are higher albedo surfaces. I probably should make a just real quick comment on that. There is some advanced research that's going on that, believe it or not, you can decouple these two things. You can actually have a dark color that, if it's engineered properly, can reflect thermal energy. But in most normal surfaces, a darker surface is storing more energy, a lighter surface is rejecting more energy. And then because of that, pavements, and therefore all horizontal surfaces, have this albedo-related effects on the climate. So they can change the local heat balance within a neighborhood, leading to either urban heating, or if it's a higher albedo, reducing that urban heating effect. Irrespective of where that surface is located, we have this radiative forcing effect. That is, again, how much we're rejecting back out of the atmosphere. If there are buildings nearby, that change can lead to changes in how much energy is used by those buildings. And finally, no matter where it's located, a change in a pavement surface can change the fuel consumption of vehicles. We've observed that in actual application, higher albedo surfaces can cool the neighborhood or can lead to surface temperatures that are almost approaching 30 degrees difference. I would say probably an average difference is in this 10 to 15 degree difference, which is definitely meaningful in terms of local energy consumption. And finally, what we have basically found is that when we make this switch from a conventional dark pavement to a cool pavement, this can lead to substantial overall climate benefits. So we can see several degree cooler local neighborhood temperatures and considerable reductions in terms of the greenhouse gases that are associated with those pavements. So hopefully this is some new information, some useful information. I do want to reiterate before I hand it off to Corey, most of our research in this space has focused on roads, but many of these effects are applicable to any horizontal surface, right? So if we have a courtyard, a paved area that's next to a building, hopefully there's not too many cars driving on it, so that part wouldn't apply, but these other effects are all quite meaningful to it. So with that, I'm going to hand it back over to Corey here, who's going to talk a little bit about what are some of the techniques for making these surfaces.
Okay. Thanks, Randy. That's really cool. Before I get into this, I want to go back to one point that Randy made. If you look at the bottom, just changing your albedo, that's a huge impact per square yard of pavement. Right? Have you thought about how you build your roads and how you build your parking lots outside of the buildings we're building? That right there, well, later we're going to have a presentation where we talk about embodied energy of concrete, right? That's somewhere between 10 to 20% reduction in the embodied energy per cubic yard of concrete. That's a pretty big impact. That's a huge impact. So you may be saying, okay, so I'm a pavement engineer by trade, okay? So part of my job is to help you figure out, all right, well, how do we do this and how do we do it cost effectively, right? There are many different ways, many different things that we need pavements for, whether it's your airport runway, right? It's the parking lot to the store that you may be shopping at. It could be your local residential street, your highway, what have you, right? So there are a lot of different tools in our toolbox from an engineering perspective on how to build these and build them cost effectively. We have many different tools that are available to us. We have a lot of existing pavements out there, right? You have an existing roadways that need maintenance. And there are tools in our toolbox to be able to cost effectively rehabilitate those roads, change the albedo of those roads or of those parking lots so that they can now reduce that carbon footprint that we're having the impact to our global environment. Some tools that I like to talk about are what we call a mill and fill. You're going to have to mill that existing pavement up, right? Because it needs maintenance anyway. Typically, if you're going about 4 inches or more to that existing pavement, you can replace it with concrete cost effectively and change the albedo, because you're going to be changing the albedo no matter what you do, right? If you're going to put an asphalt overlay on it, you're actually going to be reducing that albedo and causing it to be worse in this case, right? So if you're going to do a mill and fill 4 inches, you can replace it back with concrete and do that very cost effectively. We've done that a number of roads here in California for public roadways. Another technique that we have is what we call an overlay, where we literally actually pour concrete directly on top of your existing asphalt structure. Okay. Now the challenge with that is you're going to increase the elevation of your pavement, so you may have some drainage issues with that, and that's why I start with the mill and fill option first, because you're not changing your pavement elevation. But that is an option where we're able to go in and, like I said, put an overlay on top of that. Typically, you're adding about a minimum of about 3 to 4 inches to do that. So drainage-wise, it can be a bit of a challenge. Some other tools that we have available to us is a product called roller compacted concrete. And what's really cool about that is we put concrete pavements down with an asphalt paving machine. And you can actually open your road to traffic. We've done it within 24 hours where we open it up. We've even built a road up in Santa Rosa, California, where we had vehicles accessing driveways right behind the paving machine. So when it comes to working in an urban environment, we've got a lot of tools available to us to make it work. And so part of my job is to help you figure that out. So if you're saying, hey, how do I do this? Visit with me after. I can talk to you about any specific project you have and some of those challenges and what tools we might have in our toolbox to do that. We want to finish off with just an example of what we've done with Caltrans. This is a cool little project that we did. This is at Caltrans headquarters in Sacramento. They had an existing parking lot for their executives, right, that are entering into their building, and it needed maintenance. And so we went into it's not a really big parking lot, it's a pretty small one, right? It's a congested area, but they definitely wanted to change the albedo and measure it and document the impact that they had in this parking lot. And so we worked directly with them. We helped them generate the plan sheets, figure out all the drainage issues that they had to do, to where we went in, we removed the asphalt and then went back in with 5 inches of concrete. We were going to do the overlay option, but we had some drainage and some slope issues that we couldn't get resolved. But you'll notice, accounting for your offset of this albedo over 30 years, we're able to reduce the embodied energy, right, of that by 47%. It's pretty amazing. And then if you compare it to, they have an asphalt parking lot directly across the street. So they went out this summer and measured it, right? They measured the surface temperatures of both parking lots right adjacent to one another, and they had a 16.5 degree Fahrenheit temperature difference, right? So this absolutely matters. I don't know how many of y'all walk your dogs, but people put shoes and socks on dogs so that they don't burn their feet. When my kids run out in the street, right? Randy already mentioned this is a really important thing that we haven't paid much attention to. We paid attention to it because we were having to put socks on our dogs, but we haven't paid attention to it as it relates to global warming and that impact. So with that, what we're going to do is take questions from the audience. or discussion if you'd like, whatever you have, and Randy and I will sit here and help y'all answer that. So we've got a microphone there, Randy.